It's a pleasure to have Noga Alon with us for the theory seminar this week. Noga is a professor in the math department and also at Tel Aviv University. And those of you who don't know him, shame on you, he's been active for a very long time in all aspects of combinatorics and theoretical computer science with maybe more than 300, 400 publications. And not only the number, but they're very all those that I read have a very beautiful idea in them, so it's a real pleasure to have you, Noga.
Okay, thank you. Thanks, Lad. Thank you all for coming. It's always a pleasure to be here, especially now that it's within short walking distance from my office. So let me thank the organizers for the invitation. Thank you all for coming, even if it was mainly for the food. But still, and I'll talk about sparse universal graphs, and let me tell you what I mean by that. And of course, that's usually the case in this seminar. But let me say it explicitly: is that feel free to interrupt me and ask questions whenever something does not make sense. So here are the basic structures in the lecture. So we'll have graphs. All my graphs will be finite and undirected. I denote always a graph by a pair, VE. V is a set of vertices, E is a set of edges. So this graph has 5 vertices and 6 edges. And then I'll have the notion of a subgraph. So this is what you see here in red. We take part of the vertices and part of the edges, and we just make sure that this is a graph. Namely, if we took an edge, then we have to take its endpoints also. Of course, you all know this. And then there is the notion of an induced subgraph. So here we take a set of vertices. These are the red vertices. And we have to include exactly all the edges that have 2 endpoints among the vertices we took. So the graph we saw before, the subgraph we saw before, is not induced because we had to take this nearly vertical edge, but we didn't, and this graph is induced. Okay. So what do we mean by universal? We say that graph G is universal for a family. In my case, it will always be a finite family, although these questions make sense for infinite families as well, but we'll talk about finite. So graph G is universal for a family F of graphs if it contains every member of F as a subgraph, just as a subgraph. So we want, and the basic question about these universal graphs is we want to find sparse universal graphs for interesting families of graphs. Namely, we want to determine or estimate the minimum possible number of edges of a universal graph for some given family of graphs with most k vertices. Let's say all planar graphs with most k vertices, or all graphs with most k vertices, maximum degree at most 3, or other families. And in the 80s, when some of us were younger, and most of you didn't exist, so then it was common to say that the motivation is VLSI circuit design, because the idea is that we have some fixed wiring, right, and economical wiring, and then we can simulate with it a large number of desired wirings. But I guess now it's probably better to say that motivation is mostly historical. But still, it's an interesting combinatorial question, and
it's mostly deep learning.
Okay, sure, and it has a lot to do with deep learning. But I leave this as to the audience. Okay, so just I listed this is some partial list of previous work, and so there are lots of papers about sparse universal graphs for forests. We want a graph without too many edges that contains all the forests at most k vertices, or all the bounded degree forests, or at most k vertices, and again, this is just a partial list. Then people considered planar graphs, and more generally graphs with small separators. This will not be important, so I'm not going to even define what I mean by separators. Probably many of you know it, but this I just want to show that people looked at many families. Here is another one, just a family of all graphs with at most k edges. So we want to that our graph will contain a clique on square root k vertices, and it also has to contain a matching of k edges, and it has to contain everything that's in between, and we want the minimum number of edges. Here is another one, graphs with maximum degree at most d. So it's quite a lot of work about these. And one thing that I want to mention, and it will feature also in the second part, the longer part of the talk, when I'll talk about induced universal graphs, is that the methods that are used here are mostly a combination of probabilistic techniques and some explicit combinatorial constructions. So this is what I wrote here, that some of the results are proved by considering some random graphs. And of course, a best known model of random graphs is a Erdős-Renyi model. So here you see Erdős and Renyi. And what I usually say is that this is called the Erdős-Renyi random graphs model because it was introduced by Gilbert. And actually, it was really introduced by Gilbert a little bit before Erdős and Renyi. And their model was a little bit different than the binomial random graphs that we consider today. But somehow it makes sense to call it Erdős-Renyi because their model was very similar, and they prove lots of the fundamentals. Could, that's right, and the P, right? Okay. So Gilbert is a Gilbert from the Gilbert-Varchamov bounding encoding theory. So he's right. He's okay, and here is I just want to give one example where the upper bound of the construction that we know is probabilistic. So this is this thing about the minimum possible number of edges in a graph containing every graph with at most k edges, right? So all the graphs with most k edges on any number of vertices. So this minimum is up to constant k square over log square, log k square, and I'll not really show it, but let me just say that the upper bound is proved by considering certain random graphs with log k blocks. So you have many blocks, and you have to specify for each block what is the size of it, how many vertices it has, and what is the density that you take edges between every between every pair of blocks. And if you choose the parameters right, then it can be shown. So like a log k partite, right? Yeah. So it means all the edges between, maybe besides one block has to be a clique, all the other blocks are independent sets, and then there are some random edges between them, and then you have to show that it indeed contains everything. And then I gave also one example of some results that are proved by some explicit construction. So this is with Mike Capalbo. And this is a construction of a graph with k to the 2 minus 2 over d edges up to a constant, which contains all the k vertices graphs with maximum degree at most d. And this is tight by some counting argument. So the lower bounds often come just by counting. You know, you try to be universal for many graphs, and you don't have so many subgraphs. So the number of subgraphs you have has to be at least the number of graphs in the family, and then you just do the obvious computation. This usually gives a good lower bound. And the construction here is some properly defined product of high girth expanders. So it's not a standard product, but it's some, you take some high girth expanders, and takes the Cartesian product of the vertex set and defines the edges with respect to the edges of the expanders somehow, and this can be shown to be universal. Okay, so I'll talk more about what is called induced universal graphs. So let me tell you what is meant by this, and here I'll also tell you some motivation. Again, it will not be directly related to deep learning, but who knows? Maybe we'll see. Okay, so you can, as you can imagine, the definition is kind of is obvious. The definition was first introduced by Rado in the 60s. We call a graph G induced universal for a family F of graphs, and again, the family will be finite here. It will be graphs with at most k vertices with some property. Now we want to get every graph as an induced subgraph. Okay? So we just want to get it as a, and again, the basic question is we want a small such induced universal graph. We want now to minimize the number of vertices. Okay? So we want the minimum number of vertices in a graph that contains, let's say, every planar graph on at most k vertices as an induced subgraph, or every graph on at most k vertices as an induced subgraph, or every graph with maximum degree at most 50, right? So we can think about some families.
Why edges instead of vertices?
Yes, so here it makes, we'll soon see because of the motivation, that it makes more sense to think about the vertices. But anyway, it has to be induced graphs, right? So here, kind of the density of the graph is dictated by the way the family looks. So really the number of vertices is what we try to minimize. But this is also because of the following a very simple and still interesting connection to what is called adjacency labeling scheme. So let me say what I mean by this. When we have again a family F of k-vertex graphs, I want to define what is an L-bit adjacency labeling scheme. So formally, this is just two algorithms. In my case, they will not even have to be efficient algorithms, but let's just have two algorithms. It's better if they are also efficient. So the algorithm label gets a graph from the family, and it just assigns a label to every vertex, an L-bit label. Okay? And then the algorithm edge, it gets two labels, and as a function of the labels, it tells you if the two vertices are connected or not. But it's important, I wrote it here, that the algorithm edge only sees the label. It does not know the graph edge or the identity of the vertices. It just sees two labels. Right? And you see that this labeling scheme is a convenient way, let's say, to store a graph in our computer, right? Because we just have to remember a label for each vertex. And then when we want to know if two vertices are connected or not, we want the information about the graph, we look at these two labels and see if they are connected or not. So this is obvious. And a simple motivation still, it's a very nice one by Kanan, Or, and Rudish, Sampath, Kanan, Monin, Or, and Stephen Rudish, is that F has an L-bit adjacency labeling scheme if and only if there is an induced universal graph G for F with at most 2 to the L vertices. Okay? And as I said, this is just an observation, so you let me still say the quick proof. Well, if we have this adjacency labeling, then just each label is a vertex of graph, right? So if we have labels of size L, then we have 2 to the L vertices. And then the algorithm edge tells us which two labels are connected or not. And why does this contain every graph as an induced universal graph? Because every graph from the family, because every graph has a labeling. So we just give it a labeling, and we go to these vertices, and we have there this graph as an induced subgraph, right? Just by the definition of this a labeling scheme. And the converse is true also, right? Because if I have an induced universal graph for the family, then the label will just be the name of the vertex. And then when I want to embed the graph, to give labels to a graph, I look at the graph, I find it as an induced subgraph, and the labels that I give are the names of the vertices. Okay, so these two things are basically the same. Okay, this gives okay. So let me tell you about some previous work for these induced universal graphs. So again, people looked at various families. So one of them is general graphs. Maybe this one historically is the first one, maybe it's the most fundamental one. It's just we want all the graphs on k vertices, we want to get them as induced subgraphs of some graph. How big should it be? So people worked on this, then bipartite graphs with most k vertices, bounded degree planar graphs, forest, graphs of arboricity k, graphs of tree width k. Again, I don't need the definitions, I'll not, this is just to list some families. Graphs of maximum degree d, it's kind of a little bit easier for even d, and then there are some results for odd d, and graphs excluding the fixed minor, and bounded degree outer planar graphs, and actually also more. But, and then there are several cases. So actually here I listed all the families for which the size, the minimum possible size of an induced universal graph, the minimum possible size of a graph containing all members as induced subgraphs is known up to constant factors. So these are all of them. These are general graphs and bipartite graphs on at most k vertices. I'll talk a little bit more about that later. Graphs of maximum degree d for even d and for odd d. As I said, for odd d it's somewhat more complicated. Bounded degree outer planar graphs and forests. Everything is graphs with at most k vertices, right? So as we said, this corresponds also to a adjacency labeling scheme. So if we want to store efficiently a forest with most k vertices, we can use a scheme here. And I wrote here that in all this example, there is no non-trivial family for which the correct constant is known. So it's known up to a constant factor, but there is still a gap of some, like in this, maybe in this case, the gap is a factor of about 25 between the upper and the lower bound. And this is even in the cases that look pretty simple. So look, for example, graphs of maximum degree d, let d be 2. If I wrote non-trivial, for if d is 0 or 1, then it is not interesting. But for d equals 2, it's already, right, so graph with maximum degree 2 is a union of paths and cycles. Okay, so we want to contain all the paths and cycles of k vertices. And it's not so difficult to see that the answer here is linear in k. And then people tried to get the right constant. So there is a lower bound, I don't remember, of maybe 1.3k and an upper bound of 2.5k or something. So even here, although it's linear, we understand the graphs very well, and it looks very simple, then we still don't know the correct constant. And it looks that in the more complicated case, where the answer is polynomial or exponential, then maybe it would be even more difficult to get the right constant. But so we'll try to give some examples where
usually the exponent is known for sure.
So I mentioned, yeah, but in most examples, the exponent is known. There are some examples, actually, since you asked, let me mention it, something that we thought about quite a bit. Suppose you want all the Cayley graphs on at most k vertices, let's say over a cyclic group. So I just want to have all these circulants as induced subgraphs. So then the situation is very bad. So the bounds, the upper bound is like 2 to the k, and the lower bound is 2 to the square root k. So it's even the constant in the exponent is not known. But in okay, but this is one example. So it is.
Directed
yeah, and people looked at directed also, and actually, so tournaments and directed, and most of the things I'll say work for directed as well. But I said at the beginning that I'm talking only about undirected graphs, so yeah. But one can, yeah, and there are actually.
So I think the question for Cayley graphs, did people study wanting the universal graph to also be a Cayley graph? For planar graphs, you can demand that the universal graph is planar.
Right, yeah. So that's right. So usually here we don't want to assume it, but you can, yeah. You may want, and then maybe, and then of course sometimes it gets much bigger, and you can ask to be universal for a Cayley graph, maybe over the same kind of group or the same type of group, and then it could be, yeah, so then it will correspond maybe to some natural question of embedding some group in some other groups. But I don't, okay, so we didn't think about that, and I don't know anything intelligent to say about it. Okay. So I want to talk more about one basic case, and this is maybe the most basic case, and also the one with a longest history. And it's just a family of all k-vertex undirected graphs. Okay, so we denote by f of k. So this will be again the minimum number of vertices in an induced universal graph for the family of all k-vertex undirected graphs. And just to practice the definition, let me convince you that f of 3 is 5. Okay, so if we want a graph that contains all the 3 vertex graphs as induced subgraphs, we need at least 5 vertices. So why do we need at least 5 vertices? Because we have to have a triangle, and we have to have an independent set of size 3. They can share at most 1, so 3 plus 3 minus 1, so 5 is a lower bound, and here is why it is an upper bound. So this is a graph with 5 vertices. Here it contains a triangle. Here it contains a path of length 2. Right, everything is induced. Here it contains as induced one edge and one isolated vertex. And here it contains an independent set of size 3, and these are all of them, right? So f of 3 is indeed 5. And here I usually, it's a question how many times you can repeat the same joke, but let me, which is not so funny anyway, but let me say it anyway, that by now probably you realize that my PowerPoint skills are very limited, and this will be the most sophisticated animation you are going to see. So let me actually show it again. Right, so this is, okay. But, okay, good, thanks. So this is, all right, so f of 3 is 5, and we want to understand what is happening for a bigger k. So again, we want the minimum size of a graph that contains every k-vertex graph as an induced subgraph. Okay, so here is what Moon showed already in the 60s, and the bounds are pretty close. So you got a lower bound of 2 to the k minus 1 over 2. I'll soon show it. It's counting. It's simple counting. And then it gets a nice construction that is k times 2 to the k over 2. So it's by a factor of k. Wiesing was writing in the late 60s some survey with open problems that he thought are the main open problems in graph theory, and this is something he mentioned. Here is the result of Polomash and Thomason. It doesn't improve it, but they looked at the random graph. So what can we get from the random graph, gn 1/2? Okay, and they showed that if you take the random graph with k squared times 2 to the k over 2 vertices, it contains every k-vertex graph as an induced subgraph with high probability. And the nice thing is, so this is in the early 80s, it's really before people started to use seriously large deviation inequalities in the study of random graphs. And they are using only the second moment method. It's kind of interesting that with second moment you can still, you have to be clever. So you have to do something, but you can still get control on exponentially many graphs, right, on all the graphs. So it's still a little bit weaker than the upper bound of Moon, but it says about the random graph. This random graph, the result has been improved when people started to use these large deviation inequalities. So Brightwell and Koyakawa showed that it's constant k times 2 to the k over 2. I'll tell you a little bit more about, so even the right constant can be determined, and even more than that, but anyway. Then there is this nice paper by Alstrup, Kaplan, Thorup, and Zweig, and they got the correct behavior up to a constant factor. So as I said, the gap between the lower bound and the upper bound is about 25. It is different for even k and for odd k, but something like this. And And they have, there are lots of tricks here. And what I want to tell you about is this asymptotic formula. So this determines this size up to a negligible additive error term. So really the lower bound is the correct one. Again, up to 1 plus little o1. It behaves like 2 to the k minus 1 over 2. Now, this will also tell us, maybe we don't care so much, but let me also tell you that it tells us something more about random graphs, so we can understand very precisely what is happening for random graphs. So in fact, if we take the random graph Gn 1/2, it is easy to convince yourself that if you want a small universal graph for the family of all graphs on k vertices, it's better to take Gn 1/2 than Gn with any other parameters. So it's better to take every edge with probability half. This doesn't make sense, right? Because most graphs have about half the edges. So really, the minimum size is indeed by about a factor of k over e more than the lower bound, more than the minimum. And in fact, one can show the following, that you can look at the graph Gn 1/2 and ask for which k it is k universal with high probability, which is the largest k for which it contains all the graphs on k vertices. So in particular, it has to contain a clique of size k, right? And then what is written here is that for most values of k, whatever most means, but for most values of n, once the random graph contains a clique, it already contains all of them, all the graphs on k vertices as induced subgraphs. And then there are some exceptional values of n for which these two things differ by 1. So it will contain a clique of size k, but it will be universal only of size k minus 1. Okay, but the difference with very high probability, meaning with probability that tends to 1 as n tends to infinity, can be only 1. And for most values of n, in some well-defined way, it will not be even 1. It will be the same value. And I wrote here that the size of the largest clique in a random graph is known very accurately. It is known that it is concentrated in 2 consecutive values, and for most values of n in 1 value, and this value is completely understood. Again, here we talk about Gn 1/2. Right? This is not for sparser graphs. Things are a little bit different.
Occurrences of a given graph. So on average, I guess if it's random graph, it's going to be what we expect. But can you make statements about the coexistence of all these different graphs and their number, the frequency?
Okay, so you mean how many times each of them appears? So I'll say something about it, but indeed it will be nice to know a little bit more. But I'll come to it, and if it will still not be clear, then ask me. Okay, so now I want to talk about some proof ideas, and I think they are interesting. So I'll not really show details of anything, but I'll tell you the basic ideas. In this proof for this universal graph, for the family of all graphs on k vertices, and indeed the same method would work for bipartite graphs, would work for tournaments if you want directed graphs, would work for other cases as well, but let's just talk about this. So let's denote by capital F of k. This will be the family of all k-vertex graphs. And as before, little f of k will be the minimum number of vertices in an induced universal graph for f of k. And here is just the statement of the theorem. Now I wrote it with some explicit bounds for the error term. So the lower bound is 2 to the k minus 1 over 2. This Moon's lower bound, the counting lower bound, and the upper bound is this, and the error term is this times log to 3/2 over square root k. This is what the proof gives. There's no reason to think that this is, certainly not tight, but okay. So let's see the lower bound, and that will indeed lead us to some questions about the frequencies of things. So it is a lower bound, it's just counting. So suppose G is an induced universal graph for some family, f of k. I mean, here it's a family of all graphs, but what I'll say works for every family. Then the number of induced subgraphs of G on k vertices is, of course, n choose k if n is a number of vertices, right? We just have to choose k vertices. And now we look at all the induced subgraphs. Of course, their number has to be at least the number of members of the family, because in the best case, we get each one exactly one. And then the number of non-isomorphic graphs or of isomorphism types of graphs on k vertices, well, it's not more than 2 to the, it's at least 2 to the k choose 2. We first think about it as a labeled graph on k labeled vertices. For each pair, we either take it or not take it. So this is 2 to the k choose 2. And then maybe we got every graph k factorial times because maybe it does not have any automorphism. In fact, most graphs do not have any non-trivial automorphism. So really, this is a pretty good estimate for f of k. So we have that n choose k is at least what is written here, and we just do the arithmetic, and this gives a lower bound. Now, to get equality here, let's say that we want really equality. So to get really equality here, this is only if the frequencies are ideal, if G contains every graph, every member of fk exactly once. Now, normally, we don't expect that this will be possible, right, for normal families, and indeed, it can be shown, so I'll not show a proof, but it's not difficult to show, that every graph with exponentially many vertices contains some specific subgraphs exponentially many times. Okay, so we cannot, not only we cannot ensure that every graph will appear once, we also cannot ensure that every graph will appear a small number of times. Some graphs will have to appear very many times, and this is not too difficult, and what is written here is a little bit more complicated, but doesn't matter. So some graphs must appear very many times, and what we need, so if the number of vertices of our universal graph wants to be 1 plus little 1, 2 to the k minus 1 over 2, then still we can allow some members to appear more than once, but a typical member should appear a sub-exponential number of times, so 2 to the little o of k times. So indeed, somehow the frequencies are important, and indeed, because I will not be able to say much more about frequencies besides what is written here, but I don't even know to prove. I mean, it's certainly true that there is no graph, so that almost every graph on k vertices appears once. So you'd expect that some should appear twice and 3 times and so on, maybe like a Poisson distribution or something. But again, I don't know to prove anything like that, and it will be nice. So besides this fact that some graphs have to appear many, many times. Okay. So what can we do? We want to get this upper bound, which is close to the lower bound. So it's natural to ask if random graphs can help, because this is, and the short answer is yes and no, and the slightly longer answer is no and yes, so the bad news. So the bad news are the following. So if we just take the random graph, as I said, if we decide to take the random graph, then indeed we have to take the random graph with edge probability 1/2. So it doesn't pay to take something else. And it does not contain a clique of size k. I mean, as I said, it's well known what happens for the size of the maximum clique in a random graph. It will not contain a clique of size k. And in fact, it will not contain any graph with high probability. It will not contain any graph that has lots of automorphisms. And this is why, just because the expected number of copies of any such k vertex graph is very small. I mean, we have to, it will be n choose k, but it will, but we times 2 to the minus k choose 2. And then we will have to divide by the number of automorphisms, right? Because we choose k vertices, then we choose the number of ways to place the graph on these vertices. So it will be, I'm not sure if what I said was correct, but anyway. So let me say it again. So it's n choose k ways to choose k vertices. Then there are k factorial ways to place the graph on these k vertices. But if the number of automorphisms is big, then we have to divide by the number of automorphisms. So this is the possible number of potential ways to find the graph that we are looking there. And then once we decide how to place it, then the probability to have the right edges and non-edges is exactly 2 to the minus k choose 2. And if we write it down, then if we have many automorphisms, then it doesn't work. And in particular, the complete graph, or the empty graph, or anything that contains a very large complete graph, so anything that, okay. So on the other hand, there are the good news, and this is that, you see, if most graphs, as we said, do not have non-trivial automorphisms at all. So like a typical graph on k vertices does not have a typical automorphism, and then there are more ways to place it on k vertices. There are k factorial ways. So in this case, if a k-vertex graph has no non-trivial automorphisms, then the expected number of copies of it, so at least in terms of expectation, in Gn1/2 is what is written here, right, in the left-hand side, n choose k times k factorial times this. So there are n choose k ways to choose k vertices, then there are k factorial ways to place the graph there, and because there are no automorphisms, all these placements are distinct, and then the probability is that this is exactly what I'll get there is 2 to the minus k choose 2. So this will be the expected number. And if we had 1 plus log 1, 2 to the k minus 1 choose 2, then this will be roughly this same 1 plus log 1 raised to the power k, which if we choose the error term correctly will be a big number. So at least in terms of expectations, we expect to find all these graphs with very many automorphisms. Okay, so maybe we can do the following. So this will be the plan. We want to prove that there exists an induced universal graph for the family of all k-vertex graphs with the right number of vertices, so just a little bit more than 2 to the k minus 1 over 2 vertices. And this graph will consist of 2 parts, one big and one small. So the big part will be random. It will just be Gn1/2, and it will contain all the asymmetric k-vertex graphs. And I wrote here asymmetric because for some technical reasons, we will have to define it not as graphs that do not have automorphisms, but as something a little bit more complicated. But somehow the intuition should be this will be for the graphs that do not have automorphisms, because as we saw, the random is good for them. And then we will have a small part that will contain all the symmetric graphs. We have to define what symmetric means, and we have to decide how to find this small part. This is what we try to do. So let me tell you, so this is a definition of asymmetric that works. So we want to define a k-vertex graph asymmetric if it contains no induced subgraph with many automorphisms. And many here is, there is some free choice of parameters, but let's say is k raised to the power 8 square root k log k. So quite a lot of automorphisms, not exponential, but something like k to the square root k. And we want it not only for the graph itself, but also for every induced subgraph. So somehow this is important. Okay, and of course, if it is not asymmetric, then it is called symmetric. It is not, right? So note the double negation here. It simply means that it is not the case that it's not true that it is not asymmetric, right? So just this. Okay, so this is an example maybe of a symmetric graph, you see, because you have here lots of pairs and you can switch all of them independently, so there are lots of automorphisms. Okay. And then it turns out that indeed we can prove that the random part will work for all the asymmetric graphs because of this definition of asymmetric. If we choose the error term, the additive error term, to be some constant log to 3/2 over square root k, then with high probability, a graph with that many vertices will contain every asymmetric graph as an induced subgraph. And I didn't write here much about the proof, but it basically bounds the probabilities that a fixed asymmetric graph does not appear. And this is done using some high deviation inequality. Here, specific one is a Lagrange inequality, but with a little twist. So you have to apply it for the correctly defined random variable. And then there are a few pages of computation. But once you decide to do this, then it's basically standard. So this part is not difficult. Once we have the right definition of asymmetric, we know Lagrange, we define the random variable appropriately, and we can show it. So
how does the choice of parameters influence this -1/2 in the exponent? I mean, where did that come in? Because that's what you
mean the -1/2 or this? So really,
no, not the error term, the n to the k minus.
Yes. So the n to the right. So this comes in the main term. I mean here. Really, just the error term is what guarantees that the expected number of copies will be big enough to be able to handle it.
The main term would have been any parameter in the definition of asymmetry.
You are asking, okay, where would they, okay, so, right, so it would break when you apply Lagrange inequality, you have to, so it's, or maybe I would say, even if you want to use second moment, say, you would want to do something like this, because the second moment will not work if there is some dense part with lots of automorphisms. So for example, if we have a graph with a very big clique, and let's say, so a k minus log k size clique and log k vertices that are connected according to the digits, so it makes sure that there are no non-trivial automorphisms because of the connections to them. Then this graph, you will still not find it, although the expected number of it will be big because it has no automorphisms, but you will not find it because you will not find the dense part. Okay, and this comes in the computation of something like the second moment. So this is where the definition comes in this. So you have to, right. I mean, so does it...
Number of automorphisms of a subgraph, anything going to infinity would ruin your reading?
No. So, sorry, yeah, so I didn't understand the question. So it has to grow roughly like k to the square root k.
So the
right.
K, the exponent comes in here.
That's right,
okay.
Yeah, I didn't understand the question, but now I understand. Okay, right, okay. Right. Okay, so this about, now the interesting case is actually, what can we do about the symmetric graph? So here, my original thought was that we should be able to use some group theoretic results about the structures of large subgroups of the symmetric group in order to be able to handle these symmetric graphs. And let me tell you what I mean. So here is something simple or something that can be used. So this is a result of Babai, and it improves earlier results by Bochert and by Prager and Sackel. And it says, right, yeah, and here you have to ask, so this to check that you are really reading what is, so how did he manage in 81 to improve something proved in 89, but actually this is a classical result, so this was proved in 1889, right, so this is good, but it's but really this is used as checking that people are still reading the slides. So what they proved, and in fact here the earlier results would be good enough, but I mean anyway we basically cannot use it, but this is what we try to use is that every primitive, let's forget it for now, subgroup of SK, so we assume something about the subgroup. Primitive means transitive, and also something that does not preserve any non-trivial partition of the ground set into blocks. But so it's a property of a subgroup of permutation groups. So if it is big and it is primitive, and big is basically the size that we allow, all right, then it is doubly transitive. So really it maps every two vertices to every two vertices. And you see that if the group of automorphisms of a graph is doubly transitive, then it's trivial. Then the graph is either complete or independent, right? Every pair is mapped by an automorphism to every other pair. So all the pairs look the same, right? So either it's complete or it's independent. And of course, if we would have to worry only about the complete graph and the independent graph, then we would just add them. And even if we would have to worry about many more, we can still add them. So somehow the hope is that by looking at results like this, that maybe just there are few, maybe we can characterize all the graphs that have very many automorphisms, or that have subgraphs with very many automorphisms, and then we'll see what to do with them. Maybe there aren't too many of them, and for a while I was kind of struggling with this, and I talked with all my friends that work in group theory, but actually it seems, so after a while we decided that to characterize these graphs is probably hopeless, because there are many of them. So here is just a very large family of graphs with, which are symmetric according to this definition. You take, I wrote here random, or you take any graph with slightly smaller than k vertices, so a number of vertices which is slightly smaller. And then in it you take this 8 square root k log k times another log k vertices, and you replace each of them, you duplicate it by, say, an independent set of size 2, or by a clique of size 2, or by any small thing that has automorphisms, but let's say by an independent set of size 2, like you see here. So every vertex like this, we change it to 2 vertices, and they are connected exactly to all the vertices, or all the duplications of the vertices to which the original vertex has been connected. So now, of course, such a graph will have very many automorphisms, right? Because every pair, we would be able to switch it independently of every other pair. And there are many examples like this, and somehow we don't know too much about the structure. And actually, this is just one construction. So there are similar additional constructions that give many graphs with many automorphisms, and about which we will not know much. So it seems that indeed it's hopeless to characterize all of them. But somehow, luckily, and I'll not say much about it, but still it is possible to use some results from group theory. So basically, something about what is called the minimal degree of so basically, we want the results say that large subgroups of the symmetric group will contain some permutation on which we have good control on the number of fixed points. So it is, we will know something about the number of fixed points, and then apparently, although we will not understand the graph completely, and we will also know not very much about its automorphism group, but still we will know enough about it to be able to use this connection between adjacency labeling schemes and universal graphs in order to be able to construct explicitly a much smaller part that will handle all these symmetric graphs. So I'm not saying too much here, but if I would have had maybe 15 more minutes, I could have given you the impression that if I would have had 30 more minutes, you would have been able to follow. Yeah, but anyway, so it's but this basically can be done, and there is this very explicit graph with a little o. So here it will be negligible. So it will be maybe 2 to the k over 2 over k square or over k cube if you want vertices that will contain all the symmetric k-vertex graphs as induced subgraphs, and in this one we can yeah, we can describe it explicitly. Okay, so these two together will give us what we want, and as I said,
explicit construction for the other part.
yeah. So this will be the first open questions which I'm coming to now, and indeed, so this indeed is a natural question. So here is a further question. So as I said, there are many families of graphs for which we do not really understand well the minimum size of a possible size of a universal graph. And I think Cayley graphs are one nice example that really we have no idea about. But let me just mention some problems that are connected to specifically the family I talked about. So what they've asked is explicit constructions. Of course, we would want explicit, for example, if we really want to use these things as adjacency labeling schemes. We want something explicit. And indeed, for example, in the constructions for all the graphs with bounded degree, where indeed what is used is some product of expanders, then things are explicit and everything, the algorithms are efficient. So it's nice if you can get something explicit, and the old constructions are explicit, right? Right, yeah, not the k-squared, but the k times 2 to the k over 2 is simple and explicit, so even the original one. It's very efficient, right, yeah. It's almost, so maybe let's say a very simple explicit construction with 2 to the k, not 2 to the k over 2, let's say, we don't worry. It's just that for each, it's better to think about it as a labeling scheme, maybe. So for each vertex, the label will be the number of the vertex, the name of the vertex. So this is log k bits, and the row of the adjacency matrix corresponding to it, right? Then you just see, you want to see if two are adjacent, and you go away. And you see that if you do it this, then you really have everything twice. Right, because you can go look at the list of one and the list of the other, and so somehow there is a way to split it into two halves, and this is essentially what Moon is doing. So he was not talking about adjacency labeling schemes, but this is basically what he's doing. And then the loss is only this log k bits that come from the which correspond to a factor of k in the size of the universal graph, which corresponds to the name of the vertex. And in the difficult case is to get rid of this. And in these guys that I said, Alstrup, Kaplan, Thorap, and Zweig, they also do everything explicitly. It's complicated and it has lots of kind of tricks, but and then they can get rid of the k, but then they have some big constant factor. So it will be nice here to get something explicit. Here is something else. So what about the error term? If you look really at this f of k, so I want to insist again now about the minimum possible size of a graph that contains every k-vertex graph as an induced subgraph. Okay, so the lower bound is what is written here. Now I did it more carefully, but this is just what the computation gives. If you do the computation carefully, it's a little bit more than 2 to k minus 1 over 2. You can get plus k minus 1 over 2. Okay, this is, I don't know to add plus 1 here. So, and then there is upper bound, which is this. And maybe can the additive term be improved? So the lower bound, as I said, comes from the counting. And yeah, so just to get something non-trivial, more than the counting, as we said, some graphs have to appear many times, but this is not good enough to give anything because it's very few of the total number of graphs. But so we just, yeah, I don't know. So it looks that maybe it's, maybe you need more, an additional idea just to add +1 here or something, +2, which is ridiculous, but don't. Now here is another thing. It's more interesting combinatorially maybe, but since you you suffered until now, let me go 3 minutes about this because I think it's an interesting question. So this is like a new model of random graph. So and I'm asking about heating time questions for what I want to call the vertex random graph process. Okay, so let me define what I mean by this. So people looked at what they call the random graph process, but much less at this model. So this is the vertex random graph process. Apparently, independently, some other people were also suggesting to look at this model for some other problems. But anyway, so suppose you, so this is an infinite sequence of graphs, G1, G2, Gi. Now Gi has I vertices, so G1 has just one vertex, and Gi plus 1 is obtained from Gi by adding a vertex and connecting it randomly to all the previous ones. Okay, and let's say now randomly with probability a half, you can change the probability. It can depend on I, but let's do it like this. Okay, and then you can ask what is called the heating time result. So suppose we do this random graph process, and we look at it, and one can show the following: that as soon as Gn, so you look at the first n for which this graph Gn contains a clique of size k and an independent set of size k. And then the results that can be proved, and again it uses some of this machinery about group theory, that as soon as it contains a clique and an independent set of size k, then with high probability it will contain all the graphs as induced subgraphs. So the difficult ones to get for a random graph are just the clique and the independent set. So this is and in fact, also combining, so these are called heating time results, that exactly when something simpler happens and already something more complicated happens, people looked quite a lot at what they call the random graph process or the edge random graph process, where you start with an empty graph on n vertices and you just add the edges one by one in a random order. And then you ask, when does this graph become connected? So it turns out it becomes connected exactly when there are no isolated vertices. When the last isolated vertex becomes has degree 1, it becomes connected. When does it contain a Hamilton cycle? Exactly when the minimum degree becomes 2. When does it become k connected? Exactly when the minimum degree becomes k. So there are all kinds of results like that, and you would want something similar for this process. And I just mentioned here that, that this fact, together with what is called the Stein-Chen method, with some method in probability theory, shows that if the expected number of cliques in the random graphs, of cliques of size k in the random graph G½ when in vertices is lambda, lambda now can be 3 or 2 or 5 or 10 to infinity or 10 to 0, then the probability that Gn½ contains, is k universal, contains all of them, is up to a small error term 1 minus e to the minus lambda square. So really 1 minus e to the minus lambda would be the probability. The Stein-Chen method is a method that enables you to show that something behaves like a Poisson random variable. And so if a Poisson random variable has expectation lambda, the probability that it is not 0 is 1 minus e to the minus lambda. So the probability that there is a clique is this. The probability that there is an independent set is this. And because of Stein-Chen, you can show that they are basically behave like Poisson and independent. So the probability to get both of them is what is written here, and this is the probability to be universal. But it may be interesting to maybe to study this vertex random graph process and to understand its behavior better. And with this, I'll finish. Thank you.